So one thing about office hours today, there's a talk I want to go see at Pomona, so I'm going to be busy from 4 to 6. So right after class, I'll be in the cafe, and I'd say till 4, sounds good. And then from 6 on, I'll be in the lab, all right? So we left off on Wednesday talking about basically virtual memory primitives for user programs, right? And we talked about the fact, especially given the history of the paper, right? I think it was 95. It wasn't that common for operating systems to provide access to that sort of lower level virtual memory information available. The idea is virtual memory is there and it's virtual and you don't have to think about it, right? It just provides this illusion of memory. And the problem is that applications give up certain performance that they can gain by having knowledge of what's going on with the virtual memory, right? Having some control. So we talked about concurrent garbage collection and how we could use protections on pages in order to do that. And then the other thing we'll look at today is the use case of generational garbage collection. Okay, and so we'll finish this off in a few minutes, and then we'll go on to the next paper. We do have, as you probably know, admitted students visiting today, so we've got 1, 2, 3, yeah, so welcome. Okay. So generational garbage collection is a form of garbage collection that says basically, that takes note of the fact that most objects die young, in the sense that only a small subset of objects become long-lived. Okay? Many objects, they're like mayflies, right? They are born, they flit around doing a few small things, and then they die. And so a small portion of them become long-lived. So the idea is, if you separate the young stuff from the old stuff, you can garbage collect the young stuff more often and garbage collect the old stuff less often. Because if it's managed to get to a certain age, it's less likely that it's going to go away soon. All right? And in practice, this works well. So we have sort of a region. Just a second. All right, so it turns out in order for the tablet to work, it has to be plugged in on the tablet, and I fixed that. And then it also has to be plugged in all the way in the USB side too. So anyway, so we have young, and then we'll have old. And at some point, we'll have to migrate things from being young to being old, but have these separate regions. Okay. So the idea here is we have just some different objects in the young generation, some different other objects in the old generation, and at some point we'll have to promote. And then we're going to be doing garbage collection at the top much more rapidly than garbage collection in the bottom. So how do you find which are the objects in the, yeah, Brad?
So is it just after a certain amount of time it gets promoted, and then within the young generation it still does Baker's algorithm, or?
Yeah, we're going to still do a Baker's algorithm basically within the generation.
Just within,
yeah, just within. So we're going to find the live objects. Again, we're going to start with these roots. Start with the register, start with the stack, start with the global pointers. And that'll work fine. So basically, if we think of any of these, we're going to be pointing to something that is either in the young region or in the old region. Okay? And we may have pointers that go from young to old. And there may be points, so let's say this one may go into an old object, this one may go into a young object. If we get to an old object, what we'd like to do is stop, because we don't want to scan all the object. That's the whole point of separating these, is so we can not be iterating over all of these old objects and just try and stick with the young objects. So we would expect that there would be a fair number of pointers from young to old, but that there would be few pointers from old to young. Dhruv, any guesses as to why that might be? Yeah, why do you expect more pointers from young to old than from old to young?
I have a question. What does
Yeah.
it mean to have a pointer between the two different sections?
So we've got we're just saying we have the set of all objects, and we have the objects that are old and the objects that are young. So we're distinguishing them some way. And then we have a reference from one object to another. So whether it's one of the young ones or one of the old ones. That's all that really means, Brett.
Well, since the old ones have been around longer, it's just purely because they've been around longer, they could have accumulated more other objects that reference them. And since they're older, it could also mean that they're more important, and other objects need to reference it because it's at the head of like whatever process is happening or something.
So I think, yeah, it's older. There might be more references to it. I think that's perfectly reasonable. And then the other is just the order in which you create things and then reference them is you create things and then provide references to those things. So the references happen after they've been created. So they just tend to get created. We tend to have really fewer of these back here. Because if we had a mutable object, for example, if we had a mutable object, you'd never have an old object that references a young object, right? Because once it's been created, it's never going to refer back to another one. We could still have a young object refer to an old object, though, because an old object could get promoted to be old. All right. So what we want to find or limit ourselves is which of these old objects point to young objects. We want to keep track of what those are so that as we're following through our object, walking object by object to find out what's alive, we can know if we get to this object, we don't have to go any farther. Right? It might have tons of references to other objects in here, but it doesn't point over to the young object. Whereas these two don't point to the young objects. And there might be a lot of other ones that don't point to the young objects. So we're trying to limit how many of these old objects we have to look at that potentially refer to young objects. Drew.
So the ones that don't refer, are they the garbage? Which ones would you treat as garbage?
The garbage are the ones you can't get to from anywhere.
Okay.
Right? Okay, so our goal is we're trying to find the garbage in the young generation because we don't think there's that much in the old generation, or there's not much that often. We will do this just on a different schedule than here. And so the goal is don't visit every live object. Okay, that's our goal. We want to visit young objects and old objects that reference young objects. Okay? So here's what we do. We want to basically find all the old objects that reference young objects. So imagine we have a list. Okay? So we have a list of old objects referring to young objects. Okay? And we want to maintain that list. So what we'll do is we can look at our page table for all the objects in our old generation. And basically, we can catch whenever any of them gets written to. Okay? We actually don't need to know dynamically when it gets written to. We just want to know how has it changed since the last time we looked. Okay? So has this object changed since the last time we looked? How do we know whether it's changed since the last time we looked? We check and see if it's on a page that's dirty. If it's on a page that's dirty, has it necessarily changed?
No.
No. But something on that page changed. Okay. So we can look at all the objects on that page and see, do any of them cross this boundary? All right. So then the way the garbage collection works is we will take our root, right, our list of original objects. We will find what young objects those refer to and where those young objects refer to and so on. But whenever we get to an old object, we're going to stop. And then we have this list of old objects referencing young objects. We're going to consider that to make young objects live too. So either a young object is referred to from the stack or registers, or it's referred to from an old object. Now that old object might actually not be alive. It might be, I can't think of a good word for it, but it might eventually be garbage collected. But we think most old objects are still alive, and so we're going to treat the fact that this old object points to a young object as a reason to keep that young object alive. Okay? So we have this list. Last time we did the garbage collection, it was up to date. Now we need to make it up to date again. And so how will we do that? We're going to go through, hit the dirty pages, find all the objects on this dirty page, find that it refers to a young object, mark those young objects as still alive, clear out this dirty page, and then do the same thing for this dirty page and the same thing here and so on. Okay? Does the concept make sense?
So the dirty pages get updated since the last update, if you've accessed that object since the last update?
Yeah, so the dirty page, this is taking advantage of the MMU, right? So most MMUs will basically, when you do a write, if the dirty is not set, it'll set it. And they never clear it. So it's up to the operating system or the user program to clear it at the point that they want to, from then on, know when it's been dirtied. Okay.
So I've seen that in theory you can have multiple generations, so very young and then younger and then older. So
You can certainly do that.
Do you have a sense of how often one, just a simple generational garbage collecting is implemented, and then two, that multiple level generational?
I think multi-generational is more common. I don't know and I don't have a good sense of how many generations there are. I was going to say this meant, two hands full.
Yeah.
Well, yeah, 10 is, that seems like that would be a lot. So, yeah. So, yeah, go ahead.
So when do you move from young generation to old generation?
That is more about generational garbage collection and less about how do we do this specific implementation. But it's after it's lasted some time. Okay, so let's just call that some configurable or tunable time. If you look at the Java virtual machine runtime arguments you can provide, there are 1,001 you can provide controlling garbage collection. My guess is one of those will be, what's the knob for when something migrates up. And if you don't have dirty bits, you can actually simulate dirty bits. Right? If you don't have a dirty bit, it'll be a little slower, but what you could do is actually mark a page as not writable, take a page fault, and then mark it as writable, and somewhere mark it as dirty. It's really handy if your page tables have some extra bits in them, like we have in x86, right? How we're using the copy on write bit for JOS. So it's nice to have the page table entries just maintain those for you, okay, but not interpret them. Okay, so this paper is a nice introduction to the next paper, which is on exokernels. So traditionally, we have a operating system here. Let me change this. So I'm going to put some hardware at the bottom, So we have our hardware, we have our OS, and we have our app, or really apps, right? And this interface is, between the OS and the hardware, is a hardware interface, right? Kind of by default, what the hardware gives you is a hardware interface. And operating systems, in fact, as I said, I think on day one, provide some abstraction. What is one abstraction that, let's say, XV6 provides?
POSIX? Like the whole...
Well, that's a whole very complicated abstraction. I mean, it's true, because we have some simpler ones. So abstractions.
Files.
POSIX, which is a lot. Okay, files are an abstraction. What else is an abstraction? Virtual memory is an abstraction. It looks like real memory, except it's virtual, right? In the sense, so that is virtual in a lot of different ways, right? It can be very slow. So from the point of view of your application, it can be very slow, right? If your page has been paged out to disk and needs to be read, it can take you many millions of instructions to before that happens. Yeah.
Environments.
So environments. Environments like JOS environments?
Yeah.
Okay, so environments are also, say, processes. Yeah. Yeah, so that's going to be some form of abstraction. We're going to provide some form of inter-process communication. Another one I'll say is we have a virtual CPU, right? Time slicing. This idea that you get what looks like your own CPU and you use it, but actually what's happening is you're getting part of it, right? POSIX is the standard Unix API. Okay, so fork, exec, open, close, read, write, wait, all those sorts of things. Yep. So this is just the standard Unix APIs. All right. So this is one way you can abstract things. Another way you could abstract things is you could have hardware here, and you can have a hardware interface here. And then you can have, and I'm not going to name this right now, I'm going to just call this some software, and it provides a hardware interface to things on top of it. Why on earth would you want to have software that exists just to provide a hardware interface on top of a hardware interface? In fact, do we have such software that we use in our labs? Nandika. QEMU is this software. This software, the QEMU emulator, provides a hardware interface that happens to be, well, depending on what machine we run it on, either the same or different from the hardware interface we're on, right? So parts of the interface is the same, let's say, when I'm running on my Mac, running QEMU on my Mac. I've still got x86 instructions and so on. Parts of it are different, though, because QEMU says it has this amount of memory, and I have some possibly different amount of memory on my Mac, right? But advantages are you can run multiple instances. Would these be able to interact with one another? So let's actually look at, right, we have separate apps here in the traditional operating system, and we have interaction between, let's say, this application and this application running on the OS.
Not directly, but the OS can facilitate.
Yeah, the OS, commonly that would be the IPC. We're going to provide some form of way for processes to interact. So this will be some form of IPC. And the question is, can we do the same thing here? If I have QEMU running two virtual machines, can they interact with one another? Not normally, no. I mean, and I don't think QEMU would provide such a thing. So this is not common, It's true. With network communication, they could. It's outside of QEMU's control in some sense, right? It isn't necessarily going to see it as they go out on the network and come back, or even on the loop back and come back and so on. Okay. So in the left-hand side, when we've got, and I'm going to call this a VM for this software, we're going to call that a VM, right? A virtual machine. And here, we'll call this, let's say, a monolithic kernel. Okay, monolithic because everything's just all compiled into one. XV6 is a monolithic kernel, but it's not that big, right? 10,000 lines of code. As you go over the next 10 years, let's say, from XV6 to V7, and then at Berkeley, they got a contract to support TCP/IP. Right? Because Unix didn't have it. And so TCP/IP is in the kernel, and that hugely increased the size of the kernel. And more stuff goes in there, device drivers and so on, such that now Linux is, if you look at all the device drivers and everything else, I'm sure it's 1 million lines of code. Right? So a lot more than, how many orders of magnitude compared to the 10,000 in XP6? No. Linux does not come from BSD, except in spirit. Certainly, there's no direct code coming from there. So, what kind of abstractions you provide matters. There are some abstractions that make life easy for programmers. Okay? One example would be virtual memory and virtual CPU. Oh, good. I've just got an address space. I can write to this address space. I can read from this address space. It doesn't matter how much physical memory there is. Stuff just works. Virtual CPU, same sort of way, right? It just works. I don't have to know. We talked about cooperative multiprocessing earlier in the semester, where processes actually have to explicitly give up time to other processes. Okay? But it's simpler for a process not to do that, for a program just to kind of worry about itself and nothing else. So a monolithic kernel, yeah, Unix, Linux, XV6, VMS, all those sorts of things. JOS is not monolithic. Right, JOS is exokernel-ish. It's sort of like an it's exokernel inspired, I guess I would say. So if you have your own virtual CPU, right, where it looks like you're just running your stream of instructions, then it's important you don't have to have any special call to give up the CPU, right? You just run, and it will transparently be taken from you and returned to you. Now, in order for that transparency to work, we know we set a timer, right? The operating system will set a timer. When the timer goes off, what needs to happen? Jonathan. So timer goes off, what needs to happen? So what we want to stop the current process we're running, right? Well, it already stopped because we got an interrupt, right? Or we got an interrupt, it has stopped, it's paused, and we have saved what information? Registers, yep. So all of the registers, we have to save every single one of them because we don't know which registers the application was actually using or not. Okay? I'll give you an example of some registers that you are not currently saving in JOS or XV6. In fact, I won't. Katie, you give an example of some registers that JOS is not saving, and yet the applications we've seen don't care about.
The
x87, right. So the floating point this is because this was our challenge, so it wasn't as mean as it sounded. So all the floating point registers, of which there are quite a few of them, we're not saving in JOS. And that's okay because we're not using floating point in any of our programs. But if we did, it would be vital that they be saved. Because if we were in the middle of some floating point computation and we had, these registers set to this, and then we go away into our operating system, into a different program that does something different with floating point registers, and then when we return, it would be bad if those had changed out from under you, right? As far as this application is concerned, it was running, doing some floating point, and the registers just changed, right? And that's not good. So the transparency is good for programming, but it can be bad for efficiency. Because what if you're not using floating point? Do you need those registers saved? No. That's a kind of a simple example of the efficiency that we can get if the application is a little more involved. Okay? Stuff is hidden away from you. Scheduling, for instance. Scheduling of, let's say, processes is happening based on the operating system doing its best job at giving out CPU. I don't think I ever talked about, so some operating systems used to or would prioritize I/O-bound processes. Okay? In the sense that if you had a CPU-bound process would basically use its entire quantum and then get kicked out, and then use its entire quantum again and get kicked out, and so on. Whereas an I/O-bound process looks different. It gets a little bit of quantum, and it does a little bit of stuff, and then it gives up the CPU because it's going to do some I/O, right? Read or write. And so the theory is, well, let's go ahead, if we want to look at the next process to run, let's run some of these I/O ones because they're going to come back quickly, right? And every so often we'll run the CPU ones and let them take their entire amount of time. And processes can switch from CPU to I/O bound depending on what's happening in the history of their program. However, people caught on to this. So if you are preferring I/O bound programs, guess what? Programs will start doing I/O, right? They will run, let's say, until just before their quantum's about to expire, and then let me do a bit of I/O, so that I will follow the rule that the timer didn't kick me out. I chose to go out by doing I/O. And so then you'll look like I/O, and you'll get more CPU. Okay. We did see, of course, traditional kernels do a lot of funky stuff with virtual memory. Copy on write fork. You can use shared physical memory for read-only information like executables, demand paging. And then the last paper we talked about described how it can be useful to have that VM information available to programs. So it's nice if, and you could do more stuff if your application programs actually have access to, in some sense, some of the power that the virtual memory hardware provides. Okay. So we have all this abstraction. I/O, for instance, via file descriptors, instead of having separate APIs for each different kind of device. So we don't have separate APIs for our SSD versus our hard drive versus our floppy drive versus our mouse, let's say, where all those we might just use read-writes.
How do you do that with a mouse?
How do you read-write with a mouse?
Yeah, how do you write to it?
Well, I guess you won't do much writing, will you?
I mean, you could like
Yeah, the light. If you want the light to, or if you want it to maybe buzz or something, if you have haptic feedback, you write to it. Or there's the mouse that says, don't touch me, and shocks you, right? So, I don't know. So we have a bunch of indirection that's happening, right? This fundamental theorem of software engineering, that an extra level of indirection, I don't remember exactly how it goes, solves all problems. Yeah, you can solve any computer science problem with another level of indirection. So the problem is all that stuff has costs. Okay? And for most programs, maybe you don't care about that cost. But there are programs out there that care about the cost. So we have this monolith. When I think about monolith, I kind of think about the big, I don't know what it's called, parallelogram kind of from 2001: A Space Odyssey, right? The big black, that's what I think of kind of as the monolith. So our monolith has in here, we have our scheduling, we have our VM, we have our drivers, we have, what else do we have? File system, IPC. Oh yeah, networking's a big deal. So networking, including all our TCP IP, so on. And it's all there, compiled into one big program. Now, there's another way we could look at this. Right? We could look at this as, let's come up with a microkernel. And the microkernel, we say, what's the minimum that has to be in this kernel in order to support other processes that'll do some of this stuff? So let's say, for instance, have a file system process that's responsible for the file system. And it will be on top of the microkernel. And we can have, let's say, networking on top of here. And we can have drivers possibly on top of here. I say possibly because these other pieces aren't going to run at kernel mode. Okay? And so drivers may need to be in kernel mode. Okay, so those are somewhat different from the others. Maybe virtual memory. Certainly scheduling, probably.
Microkernels need to be scheduled against each other?
Actually, that's true. All these are needing to be scheduled. So, yeah. So what do we need? So what do we have in here? We have scheduling, IPC, because then we're going to want regular applications, right, on top of this that are using file system. And so they're going to need to communicate with this file system server. And the theory is you make the microkernel small. If you make it small, you can also make it fast, one hopes. And you can break stuff apart, have better security, right? If the file system goes down, it doesn't take the networking with it, for example. Not that you want your file system to go down. So we will come back to the microkernels in shortly. Abstractions hide things, right? That's part of really what abstractions do. They abstract away details. Sometimes they may be overgeneral, like the saving registers. I don't need floating point registers saved if I'm not doing floating point. They're sometimes not quite right. They're not quite, they don't map to your problem domain very well, right? Maybe you know that there's a process here that is finishing and you want to find its result and you know its parent's not going to be asking for it and so you want to wait for it. So why can't I wait for any arbitrary process to end? Like wait for a process by ID. Yes?
So something that's maybe uncomfortable with JOS is when we make the file system environment, we just, like in the kernel, set it environment type to file system, and like this seems kind of at odds with the idea that you should just be able to, you know, use a different file system for modularity. It seems like we're kind of hard coding it anyway, and like, how would this actually work?
So, question about, I mean, that's a good point about JOS, is that we hard code in the file system, but in one place, right? It's really in the place where we say this is the blessed file system because it's the one we're going to call the type file system as opposed to any other kind. So it would be very easy to change. In that sense, it's modular, right? It's not modular because we don't currently have a way to plug in more than one.
Right. I mean, if it crashed, you couldn't like just make a new one as the user.
No, not as the user.
File system from the IDE driver, then the file system wouldn't actually need to be blessed. My understanding is the main purpose of that is so that it can actually make calls to the IDE hardware.
And sometimes the abstraction break optimizations. So if you can imagine a database knows the form. So databases often will work in terms of B trees and just have blocks they want to write to disk, and they don't really want files. They just want an area of disk that they can write to, and that's often not provided. So Mach 3 was done at CMU and was probably the first big microkernel. Big, well, that doesn't sound good. The first more popular microkernel. Okay, so Mach 3. On top of it, they created a BSD Unix with different servers here running on top of it. And then on top of BSD Unix, you have applications who are none the wiser, right? All applications in this particular structure could make BSD Unix calls, and also some Mach calls were exposed. So if you wanted to use a Mach IPC, you could. Okay. This was not all that popular, but this is what Next used, all right? Which would be a footnote in history were it not for the reverse acquisition of Apple by Next. Yes?
What do you mean by there are multiple servers connected to it?
So there are multiple servers like a file server, servers that are responsible for aspects of the code in the kernel, various abstractions.
Libraries?
No, these would be separate processes. What they called servers, in the sense that, you know, yeah. So you basically, you would, in order to do a file system operation, send a message to the file system server asking it to do something, which sounds a lot like JOS, right, where we do that with a file system. Okay. So Next used this, not very popular. You drew.
Sorry, so there seems to be a microkernel Mach 3.0, then you have these servers. What's the interconnection between having that and then the BSD Unix? How do they interplay with each other? Are these like API calls?
So BSD Unix, really what has happened is we take, let's see, take the monolith and break it down into the microkernel and a bunch of pieces, and then have a library up here that talks to the pieces.
So is that like kind of system called dispatching or something?
Yeah, that's system called dispatching, except instead of just doing an interrupt, it may make an IPC call. Again, just like we're doing in JOS with file system calls. Does that help? Okay. So this is more common than it used to be because this is now the basis of Mac, OS and iOS and whatever runs on your Apple Watch and Apple TV and everything else. Yes. Okay, the problem though is the performance wasn't very good. So the performance of having these separate servers was expensive. Just like in Windows NT, they separated all the device drivers from the kernel itself under the idea of Joe Blow manufacturer who's writing a device driver shouldn't be writing code that's running within the kernel that'll crash the kernel. And that was all well and good except the performance of switching back and forth from kernel mode to non-kernel mode made it expensive, and they moved it back in. Same deal here. They still have mock, but all of BSD it's all in one address space and all compiled back together. So think of it as instead of a monolith where everything is all intermingled, it's a monolith where we have these nice blocks, but they're all compiled together into one thing. Okay.
Wait, sorry, why is that good? Like, why is that better than either of the two alternatives?
It's not. Really. It's not. So yeah, it's historical, I think, that it continues this way for the Mac. So. And it's maybe no accident that I think his name is Avi Tavanian, was roughly the CTO of Apple, right? Got brought in from Next, and he came. So he came from Next, and from here came from CMU, where he worked on, guess what? Mock. Yeah, so. Some of the things that they've learned from microkernels is you can actually make IPC fast. So there are various things one wants to do to make it fast, like copying causes things to be slower. And it forced modularity, and that's good. And having fast IPC is good for some things, like an X server, right, to be able to run X windowing systems. Problems are it needs to know about memory and processes, so it can't be super tiny. You may need a lot of IPC, and so any overhead in that IPC can make it quite slow. And it's hard to split stuff up, and it's hard to break stuff apart. So I'll give you an example. Let's say you want your file system buffer cache to be integrated with the VM pages, let's say. So you want some knowledge back and forth there. You know, you want some interaction, and so it's hard if they're in the same servers. So. Some embedded OSs are strongly microkernel. And in fact, if we look at an iOS device, we have two microkernels. We have the mock, microkernel with other stuff put back into it, such as this large again. But then we also have, I believe they have a, let's see, I wrote it down here. They have, yes, there's a secure enclave coprocessor. This, I think, stores the keys, I believe. And that is itself running an OS. So it runs L4 OS, okay, which is a microkernel. The L4, by the way, said for mock, hey, let me look at this. Mock is way too big and too slow. And so came up with a super cut down, all written in assembler OS with an order of magnitude faster IPC. And so that is used, as I say, on a lot of embedded systems. All right, so 1995, microkernels have been around for, let's say, 5, 6, somewhere on those years. They're relatively new. And then the Exokernel paper comes around. And the Exokernel paper is interesting because its approach is, normally when we have an operating system, at least these days and for the last many decades, we want to be able to run that operating system on multiple architectures. All right? Linux runs on x86, runs on ARM, runs on MIPS, runs on all sorts of things. And yet, the API we provide is the same across all those. Okay? So we don't have, for instance, page tables exposed in Linux. Right? One doesn't see page tables. Because if the page tables were different from architecture to architecture, that would mean somehow that that was different from place to place. So the Exokernel, the idea is, we have our hardware, we have our Exokernel, and the interface here is a hardware interface. And the interface here to, I'm going to put an application, but I'll extend that in a moment, is hardware specific. I'm not going to say it's a hardware interface, so it doesn't look like that same hardware interface. It's not a virtual machine, but it is specific to the hardware. So if my hardware has page tables, I'm going to expose page tables, for example, right? And the Exokernel's job is to do the minimal possible to allow multiple applications not to stomp on one another. Okay? So do I need to provide a virtual CPU? I don't have to provide a virtual CPU. I can say, instead of application A starts, and when the timer goes off, we transparently stop it and start a new one. Instead, I can start this application running, and when the timer goes off, say to it, hey, I would like the CPU back, please. Okay? Now, we do have to account for the fact that it may be a bad application, right, that does not give the CPU back. But if it's a good application, when we ask it to give the CPU back, it will look and it will say, I'm going to be leaving my application. When I return, I better save what I need for return. Okay? And it chooses exactly what it wants to save, right? And that can be dependent on like where it is. Maybe it's in an idle loop, and it doesn't need to save anything but one register. Okay? But maybe it's in the middle of some floating point computation, and it needs to save the floating point state too. So one of the ideas of Exokernels is don't do stuff transparently. Always involve the application and tell the application what's going on. So that means, for example, don't give the application a bunch of physical pages of memory. If the applicant, and we'll ignore the bootstrapping issue of how it gets started, but if the application wants some memory, let it allocate. Virtual memory? No. Let it allocate a physical page if it wants it. This is similar in JAWS to, don't we have a syspage alloc, right? And let it map it to whatever virtual address that it wants, right? With whatever permissions that it wants. All right, so we get rid of the abstractions. We don't provide address spaces, pipes, file systems, TCP. We let applications use the MMU. We'll talk about how we do that with the page tables. Use the physical memory. Use the network interface controller if they want. Okay? And what we're going to do is have a per app libOS. So the idea is, instead of actually having an application here, because this application has to be dealing with this fairly low-level interface and dealing with lots of things it doesn't really necessarily want to deal with, we put a layer here, which is actually libOS, and we have our application on top of that. libOS meaning it's an operating system in the form of a library. We'll just link in with our application. Okay, so we can have a POSIX library that provides us all the standard POSIX calls. But it's going to have a bunch of implementation here, and it's going to make then hardware-specific calls into here. So it will need to be allocating pages. It'll need to be doing mapping, and so on. It can provide then this virtual address space. It can go ahead and do paging in and out to disk if it wants. The nice thing is, if I have another application, I can use a different OS here, right? I don't have to use the POSIX OS. I can use some other OS. And I can customize it if I want to. So if I'm a database application, I can take this POSIX libOS, customize it, make it so that I have control over how data is being written to disk, or I have control over how the paging is happening in memory, so on. Questions so far? So yeah, give applications control, only do the minimum amount you have to do, and we'll have to figure out what that minimum amount is. So this is an example, again, with all the stuff in the hardware, the exokernel above it, secure binding saying the idea basically here being one application shouldn't be able to mess with the TLB for another application, or shouldn't mess with packets that were intended for another application, or shouldn't write the memory of another application, or shouldn't overwrite the disk space of another application's files. Okay? So what resources do we expose? What is the APIs to allow these applications flexibility? Can we share stuff? Can we go ahead and set up, how do we set up protections? Right? So let's say we expose physical pages, and we expose mappings from virtual addresses to physical addresses. So I can allocate a page, and I get back a physical address. I don't know where, it could be anywhere, but it's a real physical address. And then I can provide a way to write to the TLB, saying, map this virtual address to this physical address with these permissions. What checks do we need here? So in our exokernel, what do we want to check?
That the physical address is actually assigned to this.
Yeah, that'd probably be the most important thing. That the physical address that you're trying to map belongs to you and not someone else. Okay? But that's not too hard. That just means the exokernel needs to keep a list, basically, of what physical pages it's allocated and to whom.
I was a little confused while reading the paper because they kept talking about the TLB and never talked about page tables.
So let me give you a background on that. The TLB, right, is our cache of virtual address to physical address, right? We're grouped in pages, right? So that we don't have to have a huge cache. The question is, when you have a cache miss, where does the ground truth come from? And our answer in x86 is page table, right? If we don't find it in the TLB, the hardware first looks in the TLB, and if the hardware doesn't find it, the hardware then goes to the page table, takes it from there. Page tables, that's not strictly necessary. So you can imagine, and the MIPS computer does this. The MIPS computer, for example, has a TLB miss fault. Okay? And so on x86, we don't have explicit instructions to add stuff to the TLB, do we? Right? We can flush, but we don't go in and manipulate the TLB. Well, in the MIPS, that's what you do. So on the MIPS, the TLB's, the trap handler has to find the correct VA to PA mapping. How? Some software, maybe it has its own page table. It has some software mechanism to keep track of that. Okay? And then it has to evict a TLB entry and replace it. And then when it returns from that fault, the hardware will look in the TLB again. Right? And this time, it should find it, and then it goes about its business. So this this is the hardware TLB, and this is the managing the TLB. So if we have hardware that doesn't support page tables, then this makes sense of what we're doing here. We can allocate pages, and we can write to the TLB. All right?
So if you don't have page tables, do you have like multiple applications using different parts of virtual memory at the virtual address space at the same time?
Well, so we have some more freedom in what we want to do. We could choose on the MIPS to define something that looks exactly like an x86 two-level page table, right? Because it's just allocated pages of memory with particular format of stuff we have in it. We could choose to do that if we wanted, or we could use some other sort of data structure to keep track of, basically, for every process, what virtual address maps to what physical address. Okay? Indika.
So then, like, for the MMU, with x86, it like does a very specific thing when it's like going from virtual address to physical address. So, like, on a MIPS computer, like, is there an MMU, and if so,
There's an MMU, but
implementation is
it's the TLB. So all the MMU does is the TLB, and it doesn't know anything about how things get into the TLB. All it says is if I have an address, I go to the TLB. If it's not there, I fault, and when it returns, I try again. So it kind of follows the RISC approach of simple instructions and that don't do much. Yeah.
So I guess if you're not using a page table, like a two-layer page table, do you usually just use a more-layer page table, or what other data structures typically use?
You could use a hash table,
okay,
if you wanted. Page table, assuming you have, it kind of makes sense to have a two-level or in-level page table, because it saves, we've talked about the reasons why it saves memory. So it might very well be you use that. But you get to define what the entries in there are, what your page table entries are, because it's totally up to you. No hardware is ever going to look at it. So what's the app to kernel API? Well, here TLB write is the assumption that it's this kind of an architecture where we don't have page tables. We have these TLBs. Because if you do support page tables, then it makes sense that that's what an application should see, and that's what an application should be operating on, is those page tables. Because you want to be providing them an interface that is as close to what the hardware capabilities are as possible. Yeah, and we would get page faults. Please release memory is, I think, the one in fact, I even used the please, right? So please release memory. And you don't tell them which memory you want to release, right? I need some memory. Maybe even you say how much, okay? And then it's up to the application to decide what memory to release. Well, that kind of makes sense, right? The XV6, what is it? Well, we don't actually go to release memory right now. What would a general operating system use to decide what memory to release? Least recently used is the most common approach, right? So it just looks and it says these pages have not been used recently, and therefore they're good candidates to be gotten rid of. Now, if you're an application, you might have some specific knowledge of your program. You might know that you go through and have, I don't know, a bunch of pages, and you hit them boom, 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 and then you go back to the beginning, boom, 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 and back to the beginning. You actually know what page you're next going to use, right? And so it may be, let's see what happens here. This is 1, 2, 3, 4, N. And you're on 3. So you're using this right now. And some memory is needed. Well, the one that was least recently used is 4. But that's the one that's next going to be used, you happen to know. So therefore, there's quite a difference in what the application might choose to get rid of. It might get rid of 2 that it just used, because it knows, oh yeah, that's the farthest away one I'm ever going to use. Okay? And a different application might have different ideas of what's going to be used. So we can provide indications in Linux, for instance, to the operating system saying, here's the pattern I'm using of accessing memory. I'm going through sequentially, or I'm doing it randomly, right? And it can use that in carrying out its ideas of what memory to page out. But the application could possibly have better knowledge. Okay? What happens, by the way, if you say, please release memory, and the application, right, let's say you're the Exokernel, you say, please release memory, and it doesn't release it. Or it doesn't release it quick enough.
Kill it.
Kill it. You can always do that, okay? I mean, that's also possible when you're doing puppy training, but it's not the best approach, right? You could just take memory from it. What you could say is, I asked you to release this memory, and you did not release the memory. I am forcibly grabbing some memory from you, right? And as the paper points out, there's some memory that might be really bad for you to take, and so there might be a way for an application to reserve some number of pages that won't be yanked from it ever. Now, if I've taken this memory from you, it's going to be important for you to know that. So there has to be some revocation protocol, some way that I can actually tell you, you no longer have this, okay? I know you didn't choose to give it up, but you don't have it anymore. Okay?
How does the Exokernel decide which application to ask to release memory, or which applications to ask for how much memory when it needs more memory?
That's a good question, and that is interesting because that is kind of a policy question as to what you do there. You can, and I'm not sure what the right answer there is. You could imagine some levels, like please release memory if it's really easy, and I'm going to just go around to different applications and ask that, and if no, I still don't get enough, then I'm going to go in the harder one. But who? Maybe it's the one that's using the most. Hard to say. Hard to say. Okay. For the memory, right? What environment owns what pages? Yeah, we have talked about that. If you want a sparse array, you could use the TLB basically to be controlling that, just like we did in our mmap homework. Databases keep a cache of disk pages in memory. And so you don't want, like in a traditional OS where there's demand paging from disk, it might choose to take a page, you're the database, you have this page, and it's a copy of what's on disk. Okay? I have no idea I don't know that. So I come and I say, I'm going to take that page, don't worry, well, I'm not even going to tell you, but I'm going to transparently save this for you by writing it to somewhere else on disk. And then I will bring it back from disk if I need to. And you say, wait, if you just told me, I already have it on disk. Just throw it away. Okay? We talked a bit about the CPU. So the fact that the kernel needs to upcall to the app when it wants a CPU back. Right? In this case, these upcalls, instead of being registered, they're just fixed locations in the application for this particular implementation. And so it goes into the application and says, please yield. The application then saves its registers and yield. Or maybe it doesn't save its registers and yield. Maybe it runs a few instructions to give up a lock it has. And then save whatever registers it has and calls yield. And then on resumption, instead of transparently coming back, it just goes to a resume spot to give the application some control, and presumably the application is then going to restore the registers that got saved. Exokernel doesn't save or restore any registers except basically the program counter. If it's a different, so let's think about this. Well, yeah, we don't want to be running on the application stack because we can't trust it. So we're going to need a different stack for the kernel. So, yeah.
The paper talked a lot about secure binding to the way.
So let's talk about that. I'm going to skip IPC for a moment and come back and look at some of these questions that you guys had. Any work on making portable exokernel interfaces? It is somewhat of an oxymoron to have a portable exokernel interface, right? The idea of exokernel is you want to be providing, exposing capabilities of the hardware. And so that, no. If any application can schedule processes or mess with VM, how does the exokernel ensure isolation and security? So let's look at it from the point of view of memory. Right? From the point of view of memory, depending on the MMU hardware, it's basically going to allow the MMU to protect physical memory. Okay? So the exokernel sets up the MMU to ensure isolation. Okay? But it's not in complete control of it, right? The application has decided each of the physical pages is asked for, what virtual addresses they belong to. And depending on the MMU, we may have to switch page tables or flush the TLB, right? One or the other. So if we're on a page table type architecture, then yeah, we're going to switch page tables as we go between applications. If we're in a TLB architecture, we'll flush, unless it's a fancy TLB that has actual application IDs associated with it. So you say this mapping is for this application ID, and the CPU has some idea of what the current ID is. So the binding here is we're setting something up so that the hardware is going to monitor this binding from virtual address to physical address. And for MMUs, that's exactly what it's designed for. Good question.
What would that look like on hardware that doesn't have an MMU, like maybe an 88?
If you don't have an MMU, then you cannot ensure isolation.
Segments?
The MMU does segmentation. I mean, if we think of the MMU as dealing with the segmentation as well, then yeah, you still need an MMU. You still need some hardware support for preventing access to physical pages. multiplexing and packet filters, there was the question about this. So we get a packet that comes in on the network. Who should deal with it? Who wants it? And there's two questions of here. Who wants it? And let's assume only one person wants it, or only one application wants it. Here's one possibility of what we could do. When a packet comes in, we could send that packet to each library OS in turn, asking it, do you want this packet? Do you want this packet? Do you want this packet? The problem with that is that it's expensive, right? It's expensive to make this switch from kernel mode to user mode, and so our performance of our network is going to be really poor. So instead, what we say is, you know what? Each library, each application on your exokernel gets to specify what packets it wants. You can imagine a very simple case where it just uses the, let's say, the protocol in the Ethernet packet. I think there's a protocol field in there. Okay? So that one might be doing TCP and another might be doing some experimental format. But the problem is that's not very general, and usually we want more fine-grained control over that. So what the operating system in this paper did was allow you to install packet filters. So this was something that done, I think, in the late 80s at DEC. So what they said basically do is upload executable code to the kernel. So the application is going to provide some code that the kernel is going to run, but not just raw code. Yes. So imagine instead what we're going to provide is just an interpreter for a little language, a little safe language, right? Where the language might be something like, you know, look at offset blah. Maybe we're going to have a stack-based language. Push, you know, 16-bit word at offset blah. Compare to some constant. We have some ands and some ors and maybe a few other things. Okay? So we'll have a very restricted language in which to describe these things. All right? And what this exokernel did, and I think they were the first one to do this, is they actually said, okay, instead of having an interpreter that's going to interpret these sequences of code, we're going to actually generate machine code from this code. So we're going to compile this dynamically to machine code. And you know what? It turns out it runs fast. So that's the way this exokernel works. Basically, it takes an incoming packet and I'm going to say conceptually for a moment, conceptually runs each of these pieces of precompiled machine code that we know are safe because they're from this limited environment. And we have checks like these offsets don't exceed the size of the packet and so on.
In practice, what would these packet filters be looking at in the packets? Like when you open network connection, does it cause like all the packets to like have an ID in them or something so you can tell them apart for which application you're supposed to go to, or?
So it depends on the protocol, but you can imagine the source and destination port, or source destination port would be the most likely. Yeah. So, yeah. And the other thing you might be able to do is some static analysis on this to actually determine, for instance, no two packet filters will ever try to be accepting the same packet, so that we're disjoint the packets that any given packet filter can accept will never be accepted by another.
Seems kind of limited though, because the packets can only be so big, right? So if you're trying to send this code, like you can't send too much of it at a time if you also have to give instructions for how to interpret.
So I think there's a misunderstanding. So each application, one time, installs packet filters into the kernel.
Oh,
Okay? And then, well, very rarely installs packet filters. And then we have a whole slew of packets that use those. All right, I will see you on Wednesday. Again, a reminder, I'm in the cafe until 4, and then I'll be in the lab from 6 on. Lab 4C, I'm halfway through grading, so I should have that done tomorrow. And Lab 4B is done. I think that's it, thank you. Oh, one more reminder. I know this is our homework. It's new, submitting these questions. So one, not everyone submitted questions last night. You should have submitted questions last night, or a question last night. And second, the question you submit last night is the question you have about the paper. Because I can then look at it this morning and try and look at responses. You should not be answering the question with the thing you submit last night. That's the one that's due at 1 p.m. today. So there's an A and a B. Submit the A last night and the B today.